I read, I learn, I share. That is what this channel is all about. Hi everyone, welcome to my YouTube channel. Today's topic is about Microsoft Excel for everyone. But the exercise I created is for future scientists and engineers. So let's get started. So okay, here is the first exercise, modeling radioactive decay in Excel. So here is the formula of the radioactive decay. So normally radioactive decay follow an exponential law. So this is the equation. The equation is the NT, which is the quantity of the substance remaining at time t. And then over the time, the quantity of the substance will become lesser and lesser. This because of radioactive decay. So the NO is the initial quantity. So NT is it will change over the time. So the NO is the initial quantity, and then this is the lambda. Lambda is the decay constant. So it is depend on the substance, it's a constant value, and then the T is the time. So the overall equation is NT equal to NO multiplied by exponential superscript of minus lambda T. So the task is construct a worksheet that model the decay of a radioactive isotope over time, and then use some Excel function, exponential and ln function. This ln is the natural logarithm function to compute and analyze decay behavior. So compare the half-life calculation using both formula-based and logarithmic method. Explore how changing lambda affects the decay curve. So okay, we need to, I will explain something math concept which include the logarithm and natural logarithm. So what is logarithm? Logarithm is a log. So okay, this is logarithm log. Log 10, the 10 here is subscript, then x equal to y. Okay, so normally what is this mean? So okay, so this 10 here actually is the base. We call it base. So what is this equation mean is the base superscript mean power of y is equal to x. Okay, so for example 2 power of 3 is equal to 8. So now I will write this formula in the form of the logarithm. So it will become log. So the base is 2, and then the answer is x. The answer is 8. So 8 equal to y8, which is 3. So this is the general concept of the logarithm. So what is natural logarithm? Natural logarithm is called ln. ln, this is ln. So ln basically is the base here. The base can be any number, but if we say the ln natural logarithm, the base is become e. E is the constant value, it's the Euler number, which is around 2.7 something. So log x equal to y. So this is the difference. The difference is the base. So when we say natural logarithm, the logarithm is called natural. The base of the logarithm equation is e. So from here, the equation can be written as this form: e power of z equal to x. Okay, so this is the basic. So now we go through to this scientific context, which is the half-life of a substance. So what is the half-life of a substance? Is the time it takes for half of it to decay. So when you're using some math logic to calculate, it will become this ln 2 divided by the lambda. Lambda is the constant value. So okay, we can use this equation to derive to this equation. So basically this equation is the radiation decay equation is n T equal to NO, which is the initial E power of minus lambda constant. So we do some math trick here. We move the NO at here. So E so the half-life, so we saw the definition, half-life of a substance is the time it takes for half of it to decay. So it means let's say the original is 1, so the NT here, because it is calculate the time when the substance is decreased to its original half. So it is 1/2 is a half, and then the NO here we set it is a 1, so the NT is a 0.5, then equal to this E so now we change it to the log E. So we make it into an equation in terms of the logarithm, which is log E. Then this is the answer. Answer is the 1 minus lambda t. Okay, so this basically this log E we call is a ln of here. So because here is a minus, so when power of minus is mean 1. Yeah, the minus, if you want to change this minus to positive, actually this minus is equal to like this form, so it's 1 over e power of lambda t. Yeah. So because this one, the denominator is 1, so it's simply 1 over 2. And then we do some math trick, it becomes 2 equal to e power of lambda t. So now I make it as in the form of the logarithm form, which is log e 2 equal to lambda time. So the time here actually is the time that the substance has been decreased to its original half. So we just make it as t, then subscript of half. So log e2 is basically ln 2. So the time 1 over 2 is just basically ln 2 divided by the lambda. So this is the formula of the half-life. So okay, now just go through to the Excel part. So okay, and we need to calculate the NT, remaining half-life, ln of the ratio between the initial amount of the substance and the remaining substance. So NT, the equation is this equation. This one multiplied by So this is the table look like. So now we got some follow-up question. At what time does the substance reach approximately 50% of its original quantity? So reach the half-life. So this is the half-life, this is the answer. But what is unit? Okay, just ignore the unit of the time. So this is the answer, 5,728. So time we just how does the compute half-life compare to the theoretical value? What happens if you double the decay constant? If double the decay constant, and you just make a try with double decay the constant, so the half-life reduced. So you can see the half-life is reduced. So why the half-life is reduced? So because of this equation. So you see this is the half-life, and ln 2 is the constant value. So if this one is double, so this one is increased, this means the answer is decreased, so the half-life is decreased. Draw a chart. So how to answer number 2, question number 2. So the unit of the time is the year. So actually this theoretical value is mean like actually the substance used in this example is carbon. Yeah, it use carbon 14. Carbon 14 has a half-life of around 5,730. Yeah, okay, so now we proceed to the graph. Just plot time versus the NT. So basically the NT is the remaining substance. Because this is percent, so it should be everything times 100. Or we can use the formula, click this one, make it to the percent. Yeah, so now we proceed to the graph. So you see the graph, the graph here is similar to the logarithm. So basically the radioactive decay follow an exponential law. So it has some trend line, so you see the trend line linear cannot fit. If we change to the logarithm, exponential, yeah, just use the exponential. Okay, so basically, if we choose logarithmic, it cannot fit. It's because the exponential and logarithm is like in this two is in contrast. So here is the explanation. So log is basically grow at a slower and slower rate. So exponential is grow at a faster and a faster rate. So yeah, it is exponential because it's decay at a faster rate. So you see from 0%, like something went wrong. So basically this is just from 100% decay to 79, then 72, 48, 38. Okay. It's a slow like. Some math concept here. So whatever, we just proceed to the next part. So basically this is the graph. So this axis is for time, this axis is the number of the substance. So it will decay at a slower and a slower rate. So 50-50 is here. Okay, so this plus the half-life, so it's near. Yeah, this is because the data involved includes zero, so the log we cannot use the log as a trend line. So this is because the ln zero is undefined, and when we want to add the trend line, add the logarithm trend line, so a logarithm trend line model only works if x values are all positive and non-zero. Yeah, so okay, so this is the end of this exercise. We proceed to the next exercise. So just share something interesting. So the round here, so we use the round is because when they got a lot of the decimal point, maybe up to infinity, so we do round, like if we put 3, we round the decimal point 3 only to 3 decimal point. So but what if we round it like -1? So that is interesting. So -1 actually it just round back. So this is not round the decimal point, but just rounding backward, round the digit number. So -1 is we round the first digit. So this is the first, second, third, fourth. So -1 is I rounding the first. Okay, so the original. Okay, so the original is 5,728. So if we -1, because 8 is more than 5, bigger than 5, so we just round it to 30. So if we put -2, so 28 is lower than the 50. So rounding now is rounding 100, so lower than 50, so it's just 5,700. If we put 3, it will become 6,000. Yeah, it's now rounding the 1,000. So the top of 1,000 is 500. So here 728 is more than 500. So it just round to the 5, round to the 6. So this is just some fun exercise you can try. So we proceed to the next exercise. Cool. What nyama? So this is the second exercise. So the second exercise is the classic exercise. It involves one of the classic math concept with metric function. So metric function is very useful. Then one of the application is to solve linear equation. So let's say we got a system of the equation. So this is the system of the equation. They got three variables x, y, z. So we need to find out the value of each respective value x, y, z using the Excel function. So I repeat. So this is the second exercise. It involves one of the classic math concept, metric function. So this exercise is to use metric function to solve linear algebra problem. So here's a problem that given the following system of equation. So you need to find out the value of the x, y, z. So a quick explanation. So how to solve using the metric. So the metric basically is look like this one, got x value, x1, y1, z1, and so on. So we need to find out the x, y, z. So this is x, y, z. So what is the x1, y1, z1 is? X1 is the, like, for example, for the first equation, 2x plus 3y plus z equal to 9. So x1 is 2, y1 is 3, and then the z1 is 1. So x, y, z is what we need to find out. Then it's equal to 9, 13, 10. So this is the equation look like in terms of the metric function. So we simplify it like, okay, so this part, we call this part like A, and then this part we call it like X. A times X equal to B. Let's say it's call it B. So we want to find out the X. So the X consists of three values in metric function X, Y, Z. So we just make it inverse. So like A inverse of A times A. So because the left hand side times the inverse of A, the right hand side we must multiply the same thing. So basically this one we can remove because it just become 1. So the x is what we want to find out or we want to figure out is equal to the inverse of A times the B. Okay, so now we put this everything into the Excel. Let the Excel help us to calculate the everything. So it's a quick one if you're using Excel instead of the manual calculation. So if the manual calculation by hand, it will involve a lot of the paper, I think. At least it's A4 paper is okay. So this is how it look like in when we want to calculate the solving the linear equation using the metric. So this is the coefficient of metric A. So respective coefficient to x, y, z. So basically we just copy the value. So yeah, this is the equation. The respective value is 2, 3, 1, and so on. So the constant metric, so this is the constant. Constant is 9, 13, 10. So now we calculate the inverse metric first. So if using Excel to calculate, it's very simple. We just equal metric inverse. So array, we just select the array here. Because inverse of this metric will, if let's say the metric is like this, the inverse should be like this as well. So if let's say I delete these two rows, or okay, so I just type something at here. So you see, because the number of the cell, column, row must be exactly same to the metric A. So now the one of the cell inside the selected structure is disturbed, so it will show the split. So it means like you need to split it out, or the disturbed value you need to split it out, or just delete it, and it will show the show the whole answer. It will only show the whole answer there. So now we need to find the variable x. Variable x is in the form of include the metric of x, y, z. So we use another function, is what we call is metric multiplication with MEE-0002. So array 1 is the constant, comma, array 2 is the inverse of the metric. So okay, array 1 should be this one. I think was correct. Yeah, the array 1 should be the inverse of the metric. Yeah, so this is the exactly answer. So now we do some verification. Is let's say equal 2 times x plus 3 times y plus x. So yeah, it's equal to the 9. So yeah, this is a simple one if you're using the Excel function. But this metric function is very useful in everywhere, probably in everywhere, especially for scientists or in engineer field. So that is, we proceed to the next exercise. So here is the third exercise. So here's the question. Compare the total cost of borrowing for two individuals, Sarah and David, who take out personal loans with different principal amounts, interest rate, and loan term. So here's the question. Who pays more in interest and why? So this is some information. Average APR for personal loan, good credit. If this person got good credit, so the personal loan is 7.5. So if this person got a fair credit, so the personal loan average APR for personal loan is 15%. So APR basically is just the interest. What we call it is, so APR, the full term is annual percentage rate. So it's a figure that represents the total year cost of borrowing money, including the interest rate and all compulsory fee, expressed as a percentage. So here's the note. Later we will use the Excel to calculate to answer this question. So we will use a function called PMT. So normally it just calculates fixed monthly payment for loan based on a constant interest rate and term. So it involves you need to calculate something as well, like money rate, total pay, and the interest paid. So now let's proceed to the Excel part. So here is the table. So we need to copy paste again the question. Copy paste. Yeah, so here's the question. So 2 person, Sarah and David, principal respectively is 5,000, 3,000, APR 7.5, 15. The term is 4, one is 4, one is 3. So the monthly rate is so because this rate is the annual rate, so we just put this one times the total of month with 0.5. Fill write the formula, then total month is just the term times 12. So the monthly payment we using the PMT function. PMT, the rate is the monthly rate, then term, the unit is per month, and then the principal value. So here got the FV type, this is the optional. So what is FV? FV, what we call is the future value. So if we omit the FV argument, it defaults to 0, meaning the future value of a loan is 0. Or you can think like that, there is no outstanding balance after the final payment. So normally we just leave it, since this is the optional part. So yeah, so this is the so it's because this principal is borrowed, so that now the monthly payment actually is the monthly repayment. So it should be the minus. It should be the minus in term of the Sarah or David pocket. So when the value of money is in minus, it will show like this. It will blanket it, then will color as a red color. So it's because I want to like simplify the calculation or make the calculation more easy, I will put a minus in here. Yeah, I will put a minus in here. And because we use the PMT, so you can see it got the dollar symbol in front. So I think it's a built-in function. This is a built-in function. So total pay is simply the monthly payment times the total of the month. So total pay is around 5,800. Then the interest pay is the total pay minus the principal, so it's around 800. So we write the value, the function, so you can clearly see that. So the question is who pay more the interest. So basically Sarah pay more the interest. So why? It is probably because the principal value is because the PMT function is calculate the monthly payment or monthly repayment. So it involves 3 functions: principal, monthly rate, and the term. So you can see here is the principal. The principal loan from the Sarah is quite like a half of the David. Okay, so but the rate, the interest rate of the principal, the David pay more rate than the Sarah is almost a half. But here is I think the major effect is here the term. The Sarah is paid for 4 terms and David is paid for 3 terms. So, and then that's why the interest paid by the Sarah is more than the David. So this is just a very simple exercise, simple worksheet. So here got some follow-up question. So how does increasing the loan term affect the total interest paid? So it affects a lot. You can clearly see from this example. It's because the principal loan by the Sarah is almost double the David, but the APR, the rate by David borrowing is double when compared to the Sarah. But I think the term is the so it just affect a lot. So 4 term, even just one more year term to David, so it is affect a lot. So what happened if David refinance his loan to match Sarah APR? So we just change the value for type 7.5. So it's become lower. So you lower the APR, you lower the interest paid. So which borrower has a more cost efficient loan structure? So okay. Okay, but this question is a good question. So we figure out that Sarah pay more interest when compared to the David. But actually pay more doesn't mean like it is not cost efficient. So here got one formula. Something like interest to principal ratio. So the formula is something like this one. Interest principal ratio interest to principal. Yeah, so this one is just basically the ratio, the interest to principal divided by the principal. So just make it general. Percent, 60%, 25%. So the ratio for Sarah is 16%, but for David is 25%. So you can see the interest paid mainly affected by the monthly rate, by the term. So the more the term, the more the interest you pay. So, but it's not like that. Yeah, it is affected. The term is affected, but the most affected is the APR. So because it's double, because you can see the interest pay. Yeah, daily interest pay is lower than the SARA, but this because the principal here is much lower than the SARA. So the loan principal is much lower than the SARA. Is almost half of the SARA, is 2,000 less than the SARA. So that's why the interest pay is lower. So the term is also affected. So let's say we match the term to the daily term in terms of the year. So yeah, it is much lower. The interest rate is much lower when compared to the daily. So when we want to compare which one is the cost efficient, so this is a very important interest to principal ratio. So it will give an overview, just not simply saw the interest pay, like, because when you pay more interest, it doesn't mean like that this borrower has a less cost efficient loan structure. So yeah, this is the some interpretation of this finding using Excel. So yeah, I think this is the conclusion to this answer. Is despite. Okay, so we proceed to the next exercise. I think we just stop at here because the next exercise is something different. It's about the conditional function. So after the conditional function, we proceed to the graph part, then the VBA. So we just stop at here. And thanks for watching.